who will be speaking about adaptive fusion of multi-view for graph contrastive recommendations.
Hello, ladies and gentlemen. I'm here to represent Mengduo in Zhejiang University to give this talk. And it's about graph contrastive recommendation. And the motivation is here. Recently, graph contrastive learning has demonstrated satisfactory results on recommendation and due to its ability to enhance representation by integrating graph neural networks with contrastive learning. However, these methods often generate contrastive views by performing random perturbation on edge or embeddings, which is likely to bring noise in representation learning. Besides, in all these methods, the degree of user preference on items is omitted during the representation learning process, which may cause incomplete user-to-item learning. So to address these limitations, we propose the adaptive fusion of multi-view graph contrastive recommendation model. And to generate the informative and less noisy views for better contrastive learning, we designed 4 view generators to learn the edge weights focusing on weight adjustment, feature transformation, neighbor aggregation, and attention mechanism, respectively. Then we employ an adaptive multi-view fusion module to combine different views from both the view shared and view specific levels. Moreover, to make the model capable of capturing preference information during the learning process, we further adopt a preference refinement strategy on the fused contrastive view. And here's some related work that adopts GNNs for recommendation. And here is the overview of the proposed model. And here you can see there are 4 view generators to learn the edge weights for contrastive view construction. And then we employ the adaptive multi-view fusion module to combine the edge weights to get the contrastive view. And finally, we refine it with the preference matrix to enable the module to capture preference information during the contrastive learning process. And here is the 4 view generators. And the first is weight vector-based view generator. And the second is MLT-based view generator. The third is GNN-based, and the fourth is attention-based. And finally, after the 4 generator, we want to fuse all these different multi-views. And to effectively fuse these weights in one perfect contrastive view, here is the adaptive multi-view fusion module. And it allows flexible fusion based on different kinds of edge weights. And finally, here we present the preference refinement. And it is here to make the module capable of capturing preference information during the learning process. And we adopt this strategy to make the contrastive view maintain the preference information. And to be precise, we first compute the preference matrix, and it's about the calculating the embeddings of users in items, and we calculate the inner product. And then we refine the contrastive view with the product and introduce the refinement loss as follows. And to validate the effectiveness of our approach, we conduct very intensive experiments, and we can see the method consistently outperforms all baselines on all data sets. And for the time complexity, the method itself is comparable to the soda-based methods, and the total training time is also competitive. To validate the component of our proposed method, we conduct ablation study, and the performance of different kinds of edge weights varies across different data sets. The adaptive multi-view fusion module itself makes the fuse model more suitable on all data sets, and the preference refinement strategy further enhances performance. And then we conduct hyperparameter analysis because there are various laws, and we find that the model itself reaches best performance when increasing the first laws. And regarding the embedding size, we found that increasing it effectively enhances the model performance, and we attribute it to the better representation learning. And on the other hand, the batch size does not significantly impact the effectiveness of our model. And to conclude, the work itself proposed an effective graph contrastic learning-based recommendation model, and is named AMGCR, which employs adaptive augmentation to further improve the contrastive learning ability for recommendation. An experiment on 3 real-world data sets clearly validates its superiority. And in future work, we aim to optimize the model further, reducing its time complexity and enhancing its efficiency. In addition, we plan to delve deeper into refining learnable perspectives to advance GCL-based methods for superior recommendation performance. And that is all. Thank you.
Thank you for the presentation. We have time for a few questions. We have one from Slido. By the way, just a reminder, please use our QR code to send questions through Slido or walk up to the microphones if you feel like it. I have a question from the audience here on log WMF. Do you have an explicit negative feedback? If not, how do you label the data, distinguishing negative feedback from neutral?
Well, actually, can I show the slides?
Can you put the slides back on, please?
Oh, well, okay, thank you. Well, in our situation, we do not actually explicitly consider the negative impact. And here, the core idea of this proposed method is that in normal contrastive learning, we just add some noise or perturbations to the embeddings, and then we conduct the contrastive learning and calculate the loss. But here, we just kind of do some data augmentation and to get one embedding, and we just get the original embedding, and we calculate the loss between them. So in this way, we just try to prevent the loss and try to prevent the inaccurate representation learning, and do not just consider the negative impact.
Okay, I have 2 points here as well. Maybe you can comment on them. You have results on an ablation study and also some results on efficiency. Could you comment a little bit in terms of ablation, in terms of the interplay of the 4 different generators? I mean, how do they complement each other, perhaps, if you looked into that? And also on efficiency, is there any particular bottleneck you think is like the most obvious point to address?
Okay. Well, for the first, it's the weight vector-based view generator, and it's quite simple. Just like we have n edges between user and items, and we kind of initialize each weight to 1, and then we just do some optimization and calculate the weights. And the second is MLP-based. The intuition is that after employing the MLP model, we can do some high-dimensional feature learning. And the second is GNN-based, because our method primarily employs graph neural learning. So we kind of employ the original information in GNN. And the third is attention-based, because intuitively, for different users in different items, the importance, or we say the preference of different users to different items is different. So we kind of introduce an attention-based view generator. And for the time complexity or the bottleneck of the model, first we derive the theoretical time complexity, and we find that it actually is comparable to the current SOTA methods. And to validate it experimentally, we just from here we can say no matter is the calculation time per epoch or is the convergence epoch, it's nice. And for the total time, it is still comparable to the SOTA method. So there may be room for improvement, but now it is okay.
Okay, thanks a lot. Let's thank the speaker again.
Okay, thank you.